continuing ahead with work power energy again. So last few lectures we've been discussing about conservative and non-conservative forces. Just to quickly recap the concepts, we have seen that the general formula for work done is path integration from initial to final, and for constant force it becomes the dot product. Okay. This F dot ds integration becomes the dot product of the constant force and displacement. And we saw that conservative forces versus non-conservative forces. These are the ones where the work done is path independent. And for these ones, the work done is path dependent. Okay. We saw as examples of this, there was spring force. Okay. Any constant force. Okay. Electrostatic force, which we'll be studying later in 12th. Gravitational force. These are all examples of conservative forces, whereas kinetic friction is the most common example of the non-conservative force. Okay. Moving on from this, we saw the relationship between potential energy of a system and conservative force. We saw that potential energy for a system is defined in such a way that change in potential energy is negative of work done by the internal conservative force, okay, which is happening during that change. Yeah, I've given real life example only, Ayush, now. The example of electrostatic force, gravitational force, spring force, these are all actual real life examples only, right? So, for example, we had discussed last time that if you have a spring mass system like this, okay, spring of natural length L and spring constant K, then in order to stretch it, through a distance of x, okay, the work done by the external agent will be negative of the work done by the internal conservative force. So work done by the spring force will be minus half kx square. The work done by the external agent will be plus half kx square. And the change in potential energy of the spring, therefore, is negative of work done by the spring will be plus half kx square. So this is the change in potential energy for a spring when it is taken from x equal to 0 to x equal to x. Are you sure understood? These are all examples of real life forces only which are conservative. Okay. Similarly, gravitational force, the type of force that acts between the, for example, the moon and the earth, or any satellites orbiting around the earth, or the orbital motion of planets happen around stars, like the solar system planets are moving in elliptical orbits around our sun. So all those orbital motions are happening as a result of the real life force of gravitational attraction. Similarly, in atomic physics or in structure of atom in chemistry, you studied about electrostatic attraction, which is responsible for the centripetal force that keeps electrons in circular orbit inside atoms, right? So that's another example of a conservative force. So these are all conservative forces in general. Okay. Then after having understood about potential energy, we looked at the general form of the work energy theorem. The general statement and general form of work energy theorem, which said that the work done by external forces plus work done by any non-conservative forces equals to the change in kinetic energy plus change in potential energy of the system. This is the statement of work energy theorem. And this is what we will concentrate on applying from this point onwards when we are looking at numerical applications. Okay. Now, two special types of potential energies we'll study. Then we'll come to some problems today. I've asked you to work out questions last time from HC Verma, so we'll discuss some of those questions. So potential energy, some examples. Okay. So first of all, we will look at the elastic potential energy of a spring, how to define it. Or simply spring potential energy. Let's understand this. So as we saw last time, that whether the spring is in an extended state, okay, therefore the spring force is acting inwards and is of magnitude kx, and the differential displacement is happening outwards. Okay. Or we have a situation where the spring might be in a compressed state. So it is having a compressed length of L minus x. So the spring force is acting outwards. Okay. Whereas the displacement of the point where we are applying the force to compress it, that is inwards. So in either of these cases, you can see that for a small displacement dx, the work done by the spring force will be minus kx dx. Okay. For a small displacement dx, the work done by the spring force. Okay. So here the spring force is only the work done by the internal conservative force, because the spring force is the internal conservative force. Okay. So the change in potential energy will be equal to negative of the work done by the internal conservative force. So it is kx dx for the small displacement dx. For a small change in length dx, the change in potential energy of the spring is given by this formula. Okay. Just in general, delta U is given by negative of work done by internal conservative force. So here, this becomes negative of work done by spring force. So overall, the change in potential energy, we integrate this from whatever initial state to whatever final state, that is equal to kx dx, integrated from whatever initial state to whatever final state. So final minus initial potential energy, which is nothing but the change in potential energy, delta U, that becomes equal to half k x square integrated from initial value of x to final value of x. So that now gives us the special formula for potential energy of the spring, that U final minus U initial is half k x final square minus half k x initial square. So absolute potential energy can be given by the formula half kx square. So this simply becomes the formula of the spring potential energy. So for example, suppose we have a spring of spring constant 50 newtons per centimeter. Now I ask you, what is the potential energy of the spring? What is the potential energy stored in the spring when it is extended by 2 centimeters, or when it is compressed by, let's say, 3 centimeters? So what is the formula we'll use? You'll use this formula, that potential energy will be half kx square. In this, you will substitute x as plus 2 because it is extended in centimeters. In this, you will substitute x as minus 3 because it is compressed. But either way, you will see the potential energy of the spring will be a positive quantity because it's x square term. Okay. So make a note of this first. This is the first thing we are learning today, the relation between the state of the spring, which is x, the amount of compression or extension, and the potential energy stored in the spring, which is given by the formula half kx square. Okay. So when we are getting this formula, it is giving us the potential energy, which is a function of the state of the spring. Okay, that is the value of x. That is the meaning of this. Okay, so just make a note of this quickly. and calculate the numerical value of the potential energy in this case. In this example, calculate the numerical value of the potential energy by this formula and this form. For this part and this part by this formula. Spring constant is given to, so for the given value of the state of the spring, compression or extension, whatever, you have to just calculate the potential energy in joules. Okay, let me check your answers. So in this question, the first part you can see that we'll take x as plus 2 centimeters and the spring constant is given 50 Newton per centimeter. So we directly substitute the potential energy as half kx square. We will get it, but the unit that we will get will be in Newton centimeter. Okay, because it's Newton per centimeter into centimeter square. It is Newton per centimeter multiplied by centimeter square. Now, so that's why we'll get in this unit. So we'll get it this as 50 into 2 or 100 Newton centimeters. So that is the same thing as 100 into 10 raised power minus 1 Newton into meters. Okay, so that is sorry minus 2, my mistake. 1 centimeter is 1/100th of a meter, so this will be this much. So it will be 1 joule. Okay, Newton meter is the same thing as joule. So this is the potential energy in the first part. This is the potential energy stored in the spring. It's a positive potential energy of plus 1 joules. Then similarly in the B part, we write the spring constant once again as 50 newtons per centimeter. And it's this time compressed, so we'll write x as minus 3 centimeters, but that sign doesn't matter because potential energy is given by half kx square. So this time it is half into 50 into 3 square, again in Newton centimeters. Okay. So it's becoming 25 into 9. So that is 225 Newton centimeters, or that's the same thing as 2.25 joules or Newton meters. So this is the potential energy in this case. So just go through this carefully and let me know if the working is clear. Just a direct formula, potential energy of the spring is given by half kx square. Now I explained to you above how we get the formula also, that it's half kx square. That comes from the relationship between potential energy and internal conservative force. Yeah, that's okay, beta. But you understood the unit, na? That's the most important thing here. You can also convert this directly to SI unit first. So you can convert this K will become 50 into 10 raised power 2 Newton per meter, and X will become 2 centimeters, so 2 into 10 raised power 2 meters. So if you substitute like this, also you get the same thing. Okay. So 50 by 2 into 100 into 4 into 10 raised power minus 4. So when you work all that out, that will come out to be 1 joules. Okay, now let's look at a more interesting type of problem where we'll make use of the formula of potential energy of a spring. So let's look at a problem where there is interchange between kinetic energy and potential energy happening, because that is the most important thing for us, that how kinetic energy and potential energy might exchange, or there might be an exchange of work done between force and potential energy, or things like that. So this next example, having like this, that you have, let's say, a frictionless surface, and then there's a wall, and attached to the wall is a spring, an ideal spring, so its mass is negligible, like this. This is a smooth surface. Now there is also a block which is moving along the smooth surface at a speed v0 initially. Okay. So block of mass, let's say 2 kilograms, traveling at a speed of, let us say, 1.2 meters per second. Okay. Hits a spring or spring constant, let's say 200 newtons per centimeter. Okay. So first of all, apply work energy relation to find the block's speed v as a function of the spring's compression x. Okay, and then thereafter what we'll do is we'll make use of this to find the maximum compression the spring will undergo. Okay. And then we'll find the acceleration of the block at the instant when the spring has maximum compression. At the instant when the spring is having maximum compression, what is the speed of the block? What is the acceleration of the block? We have to find this out. Yeah. So just try this out. Apply the statement of the work energy theorem to this spring plus block as a system, and you'll see it's very easy to work this out. Okay, people. So let's figure this out quickly. So see here, what is happening is if we take one instant when the block is about to hit the spring, it's just about against the spring, but the spring is not yet compressed by the block. So यहाँ पे the speed of the block is v0 and the spring is still at the natural length state. It's not yet compressed. Okay. Now after a bit of time, let's say what has happened is the block has reached here. So the spring has got compressed, as you can see. So if the block has moved through a distance x, the spring would have got compressed by x. Okay. So the block would have reduced in speed because you can see that the spring is applying the force in the opposite direction on the block. So at this point of time, when the speed has become v, if we make a free body diagram of the block, you can see that the block is experiencing weight and normal reaction, but it is experiencing spring force in this direction. And that spring force is equal to kx in magnitude. So that is what is causing the block to decelerate as it is moving. Whereas initially when it was not in contact with the spring, at that point of time it was just moving with zero acceleration. But once it comes in contact with the spring, it starts decelerating. So you can see V has become less than V0. Okay. So now the easiest way to handle this is if we take a system as the block plus the spring. Okay. So then you can see out of all these forces, the spring force is the internal conservative force. Okay. Mg and normal reaction, you can say, are external forces. But the work done by these external forces is zero because N and Mg are both perpendicular to the displacement of the block. Okay. And there is no non-conservative force because there's no friction. It's a smooth surface. Yeah, the two diagrams are compared only ना बेटा. यहाँ से यहाँ block ने spring को x से compress कर दिया ना. So whatever the displacement of the block against the spring, that becomes the compression of the spring. Na? See, this was the natural length position when the block was just about touching the spring. So from here, if the block has moved up to here, the spring has got compressed by that much only. Na? Now this has become L minus x because this was originally L. Understood? Now, as the block is compressing the spring, it's experiencing acceleration in the opposite direction, and this force. So it's decelerating the block. So the speed will become lesser and lesser. So you can see that in the second diagram, when the spring is getting compressed, the speed of the block is reduced compared to this. Yes, Sumit, if you have a question, you can just ask me. Okay. So anyway, now coming back to this, for this system, if we apply work energy theorem, the general statement of the theorem is work done by external forces plus work done by non-conservative forces is change in kinetic energy plus change in potential energy. So here this term will be 0. Why it is 0, I've explained to you. Because normal reaction and mg, they're both acting in the direction perpendicular to the displacement. So the work done by external force is 0. Okay. Work done by non-conservative force is 0 because there is no friction, there's no non-conservative force. Okay. Now what about the change in kinetic energy? So going from this situation to this situation, A to B, you can see the kinetic energy is changing from half mv naught square to half mv square. So final is half mv square minus initial, which is half mv naught square. Whereas the change in potential energy of the spring is half kx square. The initial potential energy was 0. You can see in picture A, the speed was v naught. So the initial kinetic energy is half mv naught square. And x of the spring was 0. So the initial potential energy is 0. In the picture B, the speed of the block is v. So the kinetic energy is half mv square, whereas the spring is compressed by x. So potential energy of the spring is half kx square, the final potential energy. Okay. So the difference in potential energy is plus half kx square, whereas the difference in kinetic energy is what we've written here. It is half mv square minus half mv naught square. Okay. And the left hand side of the equation is 0 because neither there is any external agent who's doing any work, nor there is any type of friction or non-conservative force. So in fact, this situation is called conservation of mechanical energy because the work done side of the equation becomes 0. So the right hand side of the equation, which has the two energy terms, which are collectively called mechanical energy, the net change in the energy terms is 0. So we will discuss about this later. This situation is called conservation of mechanical energy, because the net change in mechanical energy, that is the change in kinetic plus potential energy, is equal to 0. That means the total amount of mechanical energy, which is the sum of kinetic energy and potential energy, remains constant. Okay, so hope you are clear up to this step here. The statement of the work energy theorem. Now, next thing all we have to do is we have to write V as a function of X from this. So rearranging the terms, you'll see the final kinetic energy is the initial kinetic energy minus half kx square. So we can write V square is equal to V naught square minus k by m into x square. So the speed as a function of x will become square root of V naught square minus k by m x square. This is the speed as a function of x, where our V naught was 1.2 meters per second, k was, V naught was 1.2 meters per second, mass was 2 kg, and k was 200 newtons per centimeter. Okay, so now from this expression we can see one more thing, and that is that when the block comes to rest, that is V becomes 0, the extension of the spring is maximum. Sorry, not extension, the compression. Okay, so from this what we will do is we will substitute V equal to 0. So the value of X we will get will be the maximum compression. So V is 0 implies that V naught square minus k by m x square should be 0. So X will come out to be V naught square root m by k, and this only is the maximum compression. This is X max. Okay, so that we can now calculate. The maximum compression will be Now substitute the values. 1.2 into square root of, now the spring constant was how much now? 200 newtons per centimeter. So that is 200 into 10 raised power 2 newtons per meter divided by the mass, which is 2 kgs. So 1.2. Oh, I just made a mistake of unit here. The unit of this speed should not be meters per second. It's too high a speed. It should be centimeters per second. Okay, just make a correction here. The unit of the speed given is not in meters per second. The unit of the speed given is centimeters per second. Okay. So when I substitute here, I have to substitute with the proper SI unit. So V naught will be 1.2 into 10 raised power minus 2 into K. This will be 200 into 10 raised power 2 divided by M, which is 2. So this will become 1.2 into 10 raised power minus 2 into 10 raised power 2. So 1.2 meters. This will be the maximum compression of the spring. Spring will still have a huge amount of compression, and that is equal to 1.2 meters. Just a minute, people. I have made a mistake of formula over here. This relation will give you X max as V naught into square root of M by K and not K by M. Okay. And we'll let V naught remain 1.2 meters per second only. So let it be the same value which I had given originally. So my X maximum will come out to be V naught, which is 1.2 into square root of M, which is 2, upon spring constant, which is 200 into 10 raised power 2, because you'll convert this in newtons per meter. Okay. Okay. So this will become 1.2 divided by 100 in meters, or maximum compression we'll get is 1.2 centimeters. Okay. So this tells us that when the block is coming at a speed of 1.2 meters per second and hits against the spring suffers a maximum compression of 1.2 centimeters. Make a note of this, please. Yes, Anjali, I'll scroll up. Now, the last part of the question, we also have to find the acceleration of the block when the spring has maximum compression. Okay. So this is here the application of work energy theorem, which is giving us the relation between V as a function of X, this one. And in that function, now we are substituting this condition that it comes to rest when the compression is maximum. So now also the third part, the acceleration of the block at maximum compression state. So that you'll understand from this. Give it an acceleration like this. Okay. So X maximum was 1.2 centimeters. So the spring force is 200 into 1.2, that is 240 newtons. So that maximum acceleration the mass was 2 kg, will be 120 meters per second square. Is the question clear to all of you? Okay. So this was an example of what we call conservation of mechanical energy, because for any system, the sum of kinetic energy plus potential energy is called the mechanical energy. Okay. Therefore, work done by external plus non-conservative forces, which is the change in kinetic energy plus change in potential energy, can also be written as the work done by external plus non-conservative forces is equal to the change in mechanical energy. Okay. The change in mechanical energy is the sum of the change in kinetic plus change in potential energy. Okay. So therefore, if work done by external plus non-conservative forces is zero for a system, that means the change in mechanical energy is zero, which means that mechanical energy is constant. So we say that this is a condition for mechanical energy being conserved. For such a case. Okay. So this is the concept of conservation of mechanical energy. Just make a note of this. I will take you back to the previous question. So first of all, the definition of mechanical energy. This is the definition of mechanical energy. It is the sum of the kinetic energy plus potential energy. Okay. And the situation where the work done by external and non-conservative forces is zero, the mechanical energy for such a system becomes conserved. Okay, let's go back to the previous solution for a minute. Not written it down fully, you can just finish up. Okay, Ayush, have you finished with this? This is clear, beta? Okay, very good. Now let's see another example of a situation like this. So it's going to be almost the same thing, but the difference is that this time we have kept the block pushed against the spring by an external force. Such that the spring is having a certain amount of compression. So this is initially. Okay. The speed of the block is 0, the acceleration of the block is 0, and the spring has a compression so initially the block is kept pressed against the spring by external force F, such that the spring is compressed through 2 centimeters. The spring has a compression of 2 centimeters. Okay. Now, given that the mass of the block is 4 kilograms and the spring constant is 25 newtons per centimeters. Okay. We have to find. Okay. Sorry. So this information is given to us. Okay. So first of all, find F. Okay. Secondly, if F is suddenly withdrawn, okay, then find the acceleration of the block the moment the force is withdrawn. At the moment when the force is withdrawn, how much will be the acceleration of the block? Just withdrawn. Okay. Then apply work energy theorem to find speed of the block at the instant when x is equal to 1 centimeter of compression for the spring. Okay. And fourth, find the speed of the block when it loses contact with the spring. Okay. The block is not attached to the spring, so it's going to eventually lose contact. So the block is not attached to the spring. That's what we are assuming here. Okay. So try this question out. You'll realize it's like just the reverse of what was happening in the first question we had discussed. There the block initially had kinetic energy and it was compressing against the spring, converting kinetic energy into potential energy as the spring was getting compressed more and more. Here is the reverse. Initially the spring has potential energy, and as the spring pushes against the block, it converts that potential energy to kinetic energy. Okay, anybody got the answer for the first part? It's very easy. If we just make the free body diagram and balance the forces, the compression in the spring is given to you and the spring constant is given to you. So just tell me how much should be the force. It's 2 centimeters, no? The compression, yeah. Kunj, your answer is correct. Hitanshu, I think you've taken the wrong value. Spring constant is 25 newtons per centimeter, and the compression of the spring is 2 centimeters. Okay, it's not 4 centimeters. Yes, Uday, correct. Yeah, so tell me the value, Hitanshu. Okay, anybody else? Yes, Uday, that's correct. 12.5 meters per second square meter, not centimeters per second square. Because see, the force you are getting is in newtons, no? So this is what the initial free body diagram will look like. Let's say this is x naught is the initial compression. Okay, when the acceleration is 0 and the speed is also 0 initially. So this is the FBD. Apart from vertical forces, which are not important here. So F is balancing Kx naught because the acceleration of the block is 0. So F is equal to 25 newtons per centimeter multiplied with 2 centimeters. So F is equal to 50 newtons. Okay, this is the amount of force. Okay. Now, when you release the force, just as at the instant when the force is removed, the spring's compression is still Kx naught. Okay. So it develops an acceleration E naught just after the force F is withdrawn. So just at that moment, Kx naught becomes mass into acceleration. Okay. So from here you can see Kx naught is 50 newtons and mass is 4 kgs into E naught. So my acceleration becomes 12.5 meters per second square. It's a very large acceleration because the spring is pushing it very hard. Okay. And now next part to understand, you have to apply work energy. So when the situation is starting, at this instant, the spring is having a compression and initial speed is 0. Okay. So here the spring is having a compression of x naught. Okay. This is just after F is withdrawn. Okay. So now after some time, if the spring is still compressed, but by a lesser amount, the compression has changed from 2 centimeters to something lesser than this now. Okay, so you can see x naught was 2 centimeters. Now this is after some time. So the compression of the spring has become less than x naught, or x has become less than 2 centimeters, but the speed of the block has become non-zero now. So between this and this, you apply work energy theorem. You take your system as the spring plus the block. So you'll see that work done by external forces is 0. Work done by non-conservative force is 0 because there's no non-conservative force. So for this system, what is happening? Mechanical energy will be conserved. So we can apply conservation of mechanical energy when we are looking at the work energy relation. Just like we're done in the first question, the same way here also, mechanical energy will be conserved. So change in kinetic energy plus change in potential energy should be equal to 0. Yeah, Kunj, that is the answer for that 1 centimeter partner. Okay, I'll just verify. So from here to here, if I'm applying work energy theorem from this diagram to this diagram, you can see that change in kinetic energy plus change in potential energy of the spring should be 0 because of these two. So change in kinetic energy is half mv square because initial speed was 0, whereas change in potential energy of the spring is half k x square minus x naught square. So I'm getting v as a function of x. This is going to be like this. This will be my v as a function of x. Okay. Where x naught was 2 centimeters. The spring constant was 25 newtons per centimeter, and the mass of the block was 4 kg. Okay. So in this only I will plug in both the things now. So at some instant, when the compression of the spring has reduced to 1 centimeter, so this will become L minus 1 centimeter. If the speed of the block at that moment is V1, okay, and then finally when the spring releases the block completely, at that time the speed of the block has become whatever final velocity because x has become 0. Okay. So from this expression only I will get both the things. Okay. So for the second or whatever, for the third part, I want to find V equal to V1 when x is equal to 1 centimeters. So use this equation. Okay, so that V1 will be square root of k by m into x naught square minus 1 centimeter whole square. So that is square root of 25 into 10 raised power 2 by 4, that is k by m, into x naught square. So that is 2 square minus 1 square. But we will multiply this with 10 raised power minus 4, so that this is now in SI unit. Okay. So 2 centimeter square is 2 square into 10 raised power minus 4 meters square. 1 centimeter square is 1 into 10 raised power minus 4. So from that we are getting this. Okay. So this V1 will come out to be 5 by 2 root 3, okay, into 10 raised power minus 1, isn't it? Because this will come 10 raised power minus 2 and this will come 10 raised power 1. So very good, Kunj, your answer was correct. Root 3 by 4 meters per second. This will be the speed at the instant when x is equal to 1 centimeters. And now next thing much more easy. Put x equal to 0 and you will get the final speed. Put x equal to 0 and you will get the final speed. So that will come, I think, 1 meter per second. Beta. Just check the value. I think it will come 1 meter per second. Or is it 1 by 4? But it should come greater than V1. No? So it should. So it should be 0.5. 1 by 2. Just check your calculation, Kunj. So for the fourth part, you want to find V final when x is equal to 0. That is, the spring has released the block completely. So it's come back to natural length shape. Okay. So put x equal to 0 in this. So V final will come out to be square root of k by m x naught square. So you can just write that as x naught into square root of k by m. So x naught is 2 centimeters. So in SI unit, it will be like this. This is 25 into 10 raised power 2 divided by 4. So 2 into 5 by 2 into 10 raised power minus 2 into 10 raised power 1. I think it should come half. So V final should come out to be 0.5 meters per second. Okay. Whereas this one, if you want to estimate it like that, it's approximately 1.73 by 4. So it's approximately 0.43. So you can see from 1 to this thing also, no? From 1 centimeter to the final, the speed has increased. So this is an example of conversion of potential energy into kinetic energy. Yeah, in the fourth part, beta, you're just putting the value of x as 0. See, in both third and fourth part, na, you're using this formula only. Na? I'm getting v as a function of x here. So यही वाला formula मुझे use करना है यहाँ पर, but यहाँ पे x का value कितना substitute किया 1 centimeter. Whereas in the fourth one, I'm substituting the value of x as how much? I'm substituting x as 0 so that I get the final speed. So substitute x as 0, you'll get this formula. Just substitute x as 0 in this. The rest is just substitution of the values. Now make sure you put all the values with SI units. Okay. Most often the mistake is with the units. The power of 10 and all, if you're taking care of it properly, you will not get the wrong answer. Okay, so this is easy enough, I'm hoping, for all of you. Understood the concept of potential energy formula of the spring and how to use it in a situation like this. Okay, done. Now we will look at another type of potential energy. So that is going to be the next formula of potential energy for us, which is going to be gravitational potential energy. Now we'll define gravitational potential energy in a very specific situation over here. We'll see how to define gravitational potential energy for a body near the Earth's surface. Okay, for a body or particle or object or whatever. Okay, near the Earth's surface. So what we mean by near the Earth's surface means that the height h above the ground level is such that it is very small compared to the radius of the Earth. RE is radius of Earth, okay, which is approximately 6,400 kilometers. So we are talking about in this particular section, we are talking about a situation where we are not taking a body to a height of, let's say, hundreds of kilometers or thousands of kilometers, only a few meters or at best a few kilometers, so that the value of its height from the surface of the Earth is negligible or very small compared to the radius of the Earth. Okay. When the height is comparable to the radius of the Earth, we have to use a different type of formula, which you will learn in a different chapter called gravitation. In this chapter, we are treating that kind of situation where the acceleration due to gravity's value is constant. Small g is constant, whereas at a very large amount of height in thousands of kilometers or even hundreds of kilometers, the value of small g becomes different from what it is on the surface. Okay. So we are not dealing with that in this chapter. We'll come to that in a different chapter. Here we are treating the situation where our small g or acceleration due to gravity is constant. So we are talking about heights which are very small compared to the radius of the Earth. Okay. So for such a situation, we can see that when a body of mass m makes a displacement of s, okay, the work done by the gravitational force is mg dot s. Okay, this is work done by the gravitational force or the weight, what we commonly call weight. Okay, now this is a conservative force. So like for any conservative force, we'll define delta U as negative of work done by the internal conservative force. So here delta U will become negative of work done by gravity. Okay. So as you know, if an object is, let's say, going by some kind of path like this from one point to another point. So point mass or an object is taken like this through a displacement, which we can now show as a vector like this, joining the initial and final position. Okay. So this is the displacement vector, and let's say acceleration due to gravity is pointing down like this. So if the displacement's components are delta x and delta y, which are the initial and final, which are the horizontal and vertical components of displacement. So here in this formula, okay, if we are taking this as our x-axis and this as our y-axis, we can take mg as minus mg j cap, because our y-axis is the vertical axis and x-axis is the horizontal axis. Okay, and we can take the displacement as delta x I cap plus delta y j cap. Okay, so from this you can see that the dot product of mg and displacement will become minus mg delta y. So from that you can see that negative of that dot product or negative of this work done will become mg delta y. So this gives us a formula for the change in gravitational potential energy. When an object is taken through a displacement of s, which has a vertical component of delta y, the change in gravitational potential energy is the weight mg multiplied by delta y. This is the formula. Okay, so just make a note of this. So when the body makes a displacement S such that the vertical component of the displacement is delta y, then we get the formula, this one. So delta y is the vertical component of the displacement. So it's an even simpler formula than potential energy of a spring, because it's not a square function, it's a direct linear function. It's directly proportional to the vertical displacement, and the proportionality is nothing but the weight. Okay, so next up, let's look at some applications of this. So the most basic application you can think of is vertical motion. For example, we have thrown up something from the ground level vertically at a speed of 50 meters per second, suppose. Okay. And after some time, it reaches here where it's climbed to a height of h, speed has become v. Okay. Find the speed v at a height h of, now we'll take the value of g as 10 meters per second square. Okay. So let's say we are taking a height of 100 meters. Okay. And secondly, find the maximum height it reaches. Okay. But we'll use work energy over here. So what we'll do is we'll take the particle plus earth as a system. Okay. So then what happens is that the gravitational force, it becomes the internal conservative force. Okay. And during this motion, there is no external force which is acting. There is no non-conservative force which is acting. So again, there is conservation of mechanical energy. Okay. Change in kinetic energy plus change in potential energy is zero. So just apply it to this situation here, which I've shown on the left. So if this is the initial time A and this is some intermediate time B, so you can see that A to B. Now, mind you, it could also be that it's coming on the way down. Okay, so this could also happen that talking about the same thing, but it's gone up and then come down. So it could have that speed V on the way down also. So let's say on the way down, it is at the point C. Okay, but it's at the same height from the ground. So change in kinetic energy is half mv square minus u square. Change in potential energy is plus mgh, because we are using the formula change in gravitational potential energy is mg delta y, where delta y is the vertical displacement. Okay, so mind you, this will also apply for A to C. C is when it's on its way down but at the same height. Okay, so this should be zero. So we will get v square is equal to u square minus 2gh. So we'll get v is equal to plus or minus u square minus 2gh. Okay. So the plus or minus will tell you whether we're talking about the point B or the point C. Okay. So either way, it's the same magnitude. So v will be plus or minus of, in this case, 50 square minus 2 into 10 into 100. Okay. So that is all right. Okay. So you can see that at B, the speed will be 10 root 5 meters per second going up, and at C, on its way down, it will be 10 root 5 meters per second coming down, but at h is equal to 100 meters, at h equal to 100 meters. Okay, so this is a very simple application of work energy theorem, where you can see that you can just use the single work energy relation instead of getting into the formula of kinematics and using the equations of motion along a straight line. You don't have to do that. You can use simply work energy theorem also here. Okay, I'll give you another example of how we can use this in projectile motion also, and you'll see it's quite effective. So at the moment, just write this down first. Okay, and work out the second part yourself. Okay, this is the first part. This is the general formula. Now for the first part, we are doing this. For the first part, we are here. We are substituting h equal to 100 meters. So we're finding the value of v, okay, at either B or C. So write this down and work out the second part of this. That is the maximum height. Yes, that's correct, Kunj. So for the second part, all you have to do is you have to put the value of V as 0. In this equation only, in this equation, which we are getting from work energy, we now want to find the maximum height. So here, V is equal to 0 at h equal to h max. Okay, so there you are. Minus half mu square plus mg h max, which just gives you the formula which you already know from kinematics. Okay, so that will become 125 meters. So this is just to get you started, but we'll see there are many type of situations. Yeah, I will send. Okay. Okay, now let's see another example of a problem which is much more easy to do from work energy. Okay. So this is a height of 20 meters. Okay. Take G as 10 meters per second square. Now a particle is given a horizontal speed of 15 meters per second and comes down in projectile motion like this, as you know. And you have to just find the speed with which it impacts the ground. Okay, find V, the speed of impact on the ground. Okay. Now, if you use work energy theorem, it's very easy. It's a one-line solution. Whereas if you use projectile motion, you'll at least have to write component equations and then solve, which is a little bit more lengthy. So take the particle plus the earth, let's say mass m, plus the earth as your system. So once again, change in kinetic energy plus change in gravitational potential energy will be 0 from A to B, because there's no external and non-conservative force acting on it. Okay, so you can see that half m v square minus u square plus mg into minus h. Because A to B, what will happen? Its vertical displacement is minus h. Because remember, the vertical axis is upwards. So the vertical component of displacement is minus h. So this should be 0. So this will give you the relation that v square is equal to u square plus 2gh. And here you will get v as square root of 15 square plus 2 into 10 into 20. Okay. So you get this speed as square root of 225 plus 400. That's square root of 625. Here v we are just taking as the speed, so we won't write it as plus minus. It's a modulus quantity. So 25 meters per second is the speed with which it hits the ground. So you can see that this type of question is a very simple application. Whereas if you had gone with projectile motion, you would have to do all this. You would have to say that, okay, along the x-axis, this is 15 meters per second, acceleration is 0. Along the y-axis, the initial velocity is 0, but the acceleration is minus 10. Okay. So we would have got Vy square is equal to Uy square plus 2Ay into y component of displacement, and Vx is equal to Ux. So in this, we would have substituted A as minus G, Ay, and Y as minus H or minus 20 meters. Okay. And Uy is 0. So we would have got Vy as this. So Vy square would have been 400 and Vx would have been 15. Okay. So then we would have said that, okay, V is equal to square root of Vx square plus Vy square, and that would have given this. But you can see it's lengthy and it's unnecessary. Once you know work energy, you don't need to do this vector analysis because you're just dealing with speed, which is a scalar quantity. So you can just deal with work energy theorem, where kinetic energy and potential energy are scalar quantities. So no need to get into vectors and components for this particular situation. Okay. Obviously, other times there is a need to get into vectors. Like if it is asked the angle with which it impacts and all that, then you need to get into the vector analysis. But if you just need to find the speed with which it hits the ground, you don't need the vector analysis. You can just do it with the one-line solution of conservation of energy. Okay. So because we are new at work energy theorem, all the examples we have seen today are applications of conservation of mechanical energy, but that will not always be the case. We will look at situations where non-conservative force is dissipating energy and external force is also doing work, and those will also be important. Okay. So that's it for today's session, people. Make sure that you revise today's lecture very carefully because we've done all applications of work energy theorem, especially the formula of potential energy of the spring and gravitational potential energy and how we have applied that in these last few problems. Make sure you understand that and continue ahead with H.C. Verma. In H.C. Verma work energy chapter now, you can go ahead in the work power energy chapter, and from the exercise questions, you can cover up to question 35 now. Okay. So next lecture, we will be discussing some of these questions. So make sure you try out questions up to 35 and discuss the doubts with me in the next lecture. That's it for today, people. Wish you all the best.